Welcome back to Basic Electronics. In the last class, we have seen how a Schmitt trigger works. We will now look at some applications of the Schmitt trigger. We will see the advantage of using a Schmitt trigger as a comparator. We will also look at the use of a Schmitt trigger in waveform generation. So let us begin. We will now look at some applications of Schmitt triggers. But before that, let us talk about comparators. What is a comparator? It has two inputs, plus and minus, and one output. If V plus is higher than V minus, then the output is high. And if V minus is higher than V plus, then the output is low. And this figure here shows the relationship between VO and V plus minus V minus. Now this relationship looks familiar to us because we have seen that in the context of an op-amp. An op-amp in the open loop configuration can serve as a comparator because of its very high gain, something like 100,000 in the linear region. This is our linear region, and as we have seen, the gain in the linear region is very high. As seen earlier, the width of the linear region, this width here, is Vsat minus Vsat divided by AV, and that is very small, something like 0.1 millivolts, and we can treat that as 0. So in short, if V plus is greater than V minus, we can say that VO is plus Vsat, and otherwise VO is equal to minus Vsat. Here is an example of how a comparator works. This is a signal Vi which is applied here. V minus is at 0, grounded, and if V plus, which is the same as Vi, is positive, then VO is high, otherwise it is low. So in this region VO is high, in this region VO is low, and so on. And these levels actually need not be plus Vsat and minus Vsat. There are comparators which can give levels of 0 and some positive voltage. But that is not important for our discussion. So a comparator can be used to convert an analog signal, for example this one, into a digital, that is high-low kind of signal, this one, for further processing with digital circuits, and we're going to look at digital circuits later. In practice, the input analog signal can have noise or electromagnetic pickup superimposed on it, and because of that, erroneous operation of the circuit may result. And let us see an example of that situation in the next slide. Alright, so this is the situation we consider. This is our input voltage, and once again we have connected the minus input to ground and the plus input to Vi. So the expected output is given here. When Vi is positive, we expect the output to be plus Vsat, and when Vi is negative, we expect the output to be minus Vsat, here as well as here. What happens in practice is that the input signal is not always clean. There could be some noise or electromagnetic pickup riding on it, and therefore the original signal might get corrupted and might look like this, for example. And because of that, instead of one transition that we expect from plus Vsat to minus Vsat, we might have multiple transitions as shown here. And let us expand this part to get a clearer picture of this situation. So let's expand that part over here. So this is our input signal, and instead of crossing 0 only once, as in this case, it is crossing it here and then here and then here again. And because of that, the output transition is not just 1 but 1, 2 and 3. And this is definitely not desirable. So what has happened is the comparator has produced multiple spurious transitions or bounces, which are referred to as comparator chatter. It turns out that we can use a Schmitt trigger to eliminate this chatter, and let us see how we can do that in the next slide. Let us now see how replacing the comparator with a Schmitt trigger helps in this situation. So here is our corrupted input signal, same as in the last slide. And now this Schmitt trigger gives us only one transition, and let us try to understand how that is possible. So once again, let us expand this part to get this Vi versus time curve here, and it has crossed 0 3 times, 1, 2 and 3, but that has resulted in only one transition in the output, that one. And let us now try to understand why that happened. So here is our VO versus VI relationship for the Schmitt trigger, and it looks a little different because our VI axis is now drawn vertically, but it's the same as what we have seen earlier. This is VTH, this is VTL, this is the high VO level, VSAT, and this is the low VO level, minus VSAT. When the input voltage is here, we are here on this VO versus VI relationship. And now what's happening? As time proceeds, this input voltage is coming down, so we are going in that direction. And when is the output going to change? The output is going to change not at VTH but at VTL. So that means the output will only change when the input voltage reaches this point, and that is exactly where this transition is occurring. Now what happens in between is not really important. Even if we had several transitions in this region, it does not really matter, because the input voltage has to cross this VTL level to produce a transition at the output. So that is how these spurious transitions are taken care of. Let us summarize. While going from positive to negative values, Vi needs to cross VTL and not 0 volts to cause a change in VO. So Vi going from positive to negative, it has to cross this point, which is VTL, and only then a change in output will happen. In the reverse direction, negative to positive, Vi needs to cross VTH. Negative to positive, so we are going like that, and now we have to cross this level VTH for the output to change. The circuit gets rid of spurious transitions, which is a major advantage over the simple comparator. The hysteresis width VTH minus VTL should be designed to be larger than the spurious excursion riding on Vi. This is our hysteresis width, and we should design it such that it is larger than these excursions which are riding on the input voltage. Then we will not have this problem of multiple transitions. We will now look at another application of Schmitt triggers, and that is to generate waveforms, in particular square wave output voltages. Here is a summary of the VO versus VI relationship for a non-inverting Schmitt trigger and an inverting Schmitt trigger. And here are the symbols. Alright, let us make a few important points. A Schmitt trigger has two states, VO equal to L plus and VO equal to L minus, L plus, L minus, L plus, L minus. With a suitable RC network connected to this Schmitt trigger, it can be made to freely oscillate between these two levels, L plus and L minus, and such a circuit is called an astable multivibrator or a free running multivibrator. An astable multivibrator produces oscillations without an input signal, the frequency being controlled by the component values such as resistance or capacitance. And we should remember that the maximum operating frequency of these kinds of oscillators is typically about 10 kilohertz, and that is because of op-amp speed limitations. As we have seen earlier, op-amp has a finite slew rate, and therefore this maximum operating frequency is limited. Let us take a look at this circuit. What do we have here? We have an inverting Schmitt trigger, and that is its VO versus VI relationship, and it's reproduced here. This is the high tripping point VTH, low tripping point VTL. L plus is the high level of VO and L minus is the low level of VO. This axis is VO, this axis is VI. VO is here and VI is here. So VI is the same as the capacitor voltage. Alright, let's take some numbers. R equal to 2K, C equal to 1 microfarad, L plus 5 volts, L minus 5 volts, VTH plus 1 volt, VTL minus 1 volt. So this is plus 1 volt here, minus 1 volt, plus 5, minus 5. And as we will discover, this circuit oscillates between high and low, and let us see how that happens. Let us start at t equal to 0 with VO equal to L plus and VC equal to 0. That means the capacitor is uncharged and VC and VI are the same. So our VC equal to VI equal to 0 and our VO is L plus. So we are right here. That is the data point that we have right now at t equal to 0. What happens now? This input current is 0. This VO is plus 5 volts. Capacitor voltage is 0. So the capacitor is going to start charging towards VO, that is plus 5 volts. And the time constant, of course, is R times C. There is only one R here, and that is 2K times 1 micro or 2 milliseconds. Note the scale here. This entire period is 10 milliseconds. Alright, so let us show this charging process. That is how the capacitor will charge. Since the time constant is 2 milliseconds, in about 5 time constants, that is 10 milliseconds, it would charge towards 5 volts. And the charging process would be almost completed. Now it doesn't quite reach there, and let us see why. Let us look at what is happening with respect to this VO-VI relationship. We started off here at t equal to 0. So our VC or VI was 0. Our VO was plus 5. And now this capacitor has started charging. What does it mean? That means VI has started increasing. VI and VC are the same. So therefore, we are moving like that. And what happens when VI crosses VTH? The output flips like that. And now what happens is this VO has become minus 5 volts and the capacitor will now start discharging and will eventually reach minus 5 volts. But again, that does not happen. Why? Because as the capacitor discharges, we are moving like that. VO is minus 5 and VI is decreasing, so we are moving in that direction. And when we cross VTL, again the output is going to change. And this process is going to result in oscillations like that. So at this point, the output changed to plus 5 again. The capacitor now starts charging again towards 5 volts like that, and so on. So this process just keeps repeating and we have oscillations. So our VO is a square wave, plus 5 to minus 5, and we get this kind of waveform for VC or VI. Note that the circuit oscillates on its own, that is without any input. There is no input anywhere for this circuit. Question: where is the energy coming from? What is the answer to that? Remember, there is an op-amp sitting inside, so that is where the energy is coming from, specifically the power supply of the op-amp. Let us now find the period of oscillation. Here are the waveforms. VO going from L plus to L minus, and VI or VC going from VTL to VTH. If you recall, in the last example we had VTL equal to minus 1 volt, VTH equal to plus 1 volt, L minus was minus 5 volts and L plus was plus 5 volts. Alright, so where do we begin? Let us consider this portion. This is a charging process and the capacitor is going to charge towards L plus, and that process can be described by this expression VCT equal to A1 e raised to minus t by tau plus B1, where tau is simply R times C. What is VC at 0? This is our t equal to 0, so VC is VTL. What is VC at infinity? At infinity, this capacitor voltage would reach L plus, so that is our VC at infinity. Now using these two conditions, we can find A1 and V1. You are supposed to do it as homework. And now let us use the condition that at t equal to t1, this point, VC is equal to VTH. So we substitute VC equal to VTH in this expression, A1 e raised to minus t1 by tau plus B1. A1 and B1 are already known from these conditions, and that gives us T1. Let us now look at the discharging transient, this part. At t equal to T1, the capacitor voltage is equal to VTH, and then it starts decreasing, and it would have gone all the way to L minus as t tends to infinity. However, that does not happen because at t equal to T2, the output voltage flips. And let us now describe this part of the transient with this equation here. Vc of t equal to A2 e raised to minus t1 by tau, and this amounts to taking this T1 as the reference or the origin, and that turns out to be convenient, plus B2. Now to find A2 and B2, we need two conditions on Vc of t. What are those two conditions? One, at t equal to T1, Vc is VTH. What about the second condition? As t tends to infinity, Vc would have reached L minus. So that is the second condition. So using these two conditions we can find A2 and B2. And now we can use the condition that at t equal to T2 Vc is equal to VTL. So we substitute VTL over here and T2 over here, and then we get VTL equal to A2 e raised to minus T2 minus T1 by tau plus B2, and A2 and B2 of course are already known from here. Alright, so with this equation we can now obtain T2 minus T1. T1 is already known and therefore we can get T2, and T2 is the same as the time period T. So let us now take a special case. Let's say that L plus and L minus are equal in magnitude. For example, this may be 10 volts, this may be minus 10 volts, and VTH and VTL are also equal in magnitude. For example, this may be 2 volts and this may be minus 2 volts. In that case, we can show that this time period, that is the period of oscillation, is given by 2 RC times log L plus Vt divided by L minus Vt, where L is this L plus and Vt is the same as VTH. Now you are encouraged of course to go through all of this algebra and arrive at this result. If you hook up this circuit in the lab, you will realize that it cannot be pushed to arbitrarily high frequencies, and that is because op-amps have a finite slew rate. For example, op-amp 741 has a slew rate of 0.5 volts per microsecond. This is the waveform obtained with op-amp 741, and as we can see, it is not as sharp as we would expect theoretically. We have these slopes here. Whereas if we use another op-amp with a higher slew rate like op-amp 411, which has a much higher slew rate, 10 volts per microsecond, then we can get sharper waveforms. So that's an important point, and we should remember that if we want to implement that in the lab or for some application. Here is another oscillator circuit that uses a Schmitt trigger. It has an integrator and a Schmitt trigger connected in a circular fashion. That is, the output of the integrator goes as the input of the Schmitt trigger, and the output of the Schmitt trigger is the input of the integrator. The VO versus VI relationship for the Schmitt trigger is shown here. It's a non-inverting Schmitt trigger. VTH and VTL are the tripping points, and L plus and L minus are the high and low output voltage levels. This axis is the output of the Schmitt trigger, and in this case it is VO2, and this axis is the input of the Schmitt trigger, and in this case it is VO1. So note that VO2 serves as input for the integrator. These are the waveforms. That is VO2, the blue one, and that is VO1. And VO1 is a triangular waveform in this case, as opposed to the capacitor voltage waveform that we saw in the last circuit. Let us look at how this circuit works. Let us start with the integrator. For the integrator, we have VO1, which is the output, equal to minus 1 over RC integral VO2 dt. VO2 is the input for the integrator, and we rewrite that as minus 1 over tau integral VO2 dt. If VO2 is positive, VO1 will decrease, and if VO2 is negative, then VO1 will increase, and that is because of this negative sign. Alright, so let us consider the case where VO2 is positive. Let's say this interval marked T1 here. So here VO1 is decreasing because VO2 is positive, and what is happening in terms of this VO versus VI relationship for the Schmitt trigger. VO2 is high, so we are here, and VO1 is decreasing, so we are going in that direction. When we cross VTL, the output is going to flip from high to low, and that is what happens here. When VO2 changes its sign, as it goes from L plus to L minus, there is a change of sign here, and therefore VO1 now starts increasing. That is what we are seeing over here. And in terms of this plot, what is happening is VO2 is negative, L minus, so that is here, and VO1 is increasing, so we are going in that direction. And now when we cross VTH, VO2 will change once again from negative to positive. So that is what happens at this point. VO2 changes from L minus to L plus, and this process keeps repeating, and that is how we get oscillations. Let us now compute the period of oscillation. What is the period of oscillation? T, that is equal to T1 plus T2. We can compute T1 and T2 individually and then add the two. And an easy way to do that is to just differentiate this equation. When we do that, we get VO1 dt equal to minus VO2 by tau. And if VO2 is constant, then we can write delta VO1 by delta T equal to mod of VO2 by tau, just taking only magnitudes here. That gives us delta T equal to tau times delta VO1 by VO2. And now we can apply that to each of these intervals, T1 as well as T2. And that gives us T1 equal to tau times VTH minus VTL, that is our delta VO1, divided by VO2. VO2 is L plus at that time. What about T2? Similar. Delta VO1 is once again the same, this difference, and VO2 is now L minus, and of course we have to take the magnitude of that, so therefore we have put a minus L minus here. So that is T1 and T2. So the period is T1 plus T2, and that gives us the frequency equal to 1 over T. Sometimes we are interested in limiting the output voltage that is produced by this Schmitt trigger, which we call VO2 in our previous slide, and that can be done using this Zener pair. And we have looked at this Zener pair and seen how it works as a voltage limiter when we were talking about diodes. When VO2 is high, let's say this is our VO2 level, the high level, then D1 conducts in the forward direction, D2 conducts in the reverse breakdown mode, and then VO3, this output voltage, is V on plus Vz, V on appearing here and Vz appearing here. When VO2 is minus Vsat, this level, then what happens is D2 conducts in the forward direction, D1 conducts in the reverse breakdown mode. So V on appears here, Vz appears here, and the output voltage VO3 is minus V on minus Vz, that level. Alright, now let us look at the purpose of R3, and that is to limit this current that we draw from this second op amp. What is the voltage that is appearing across R3? It is the difference between VO2 and VO3, either that or that, and we can calculate R3 so that the current that we draw from OA2, the second op amp, is within its current limits. Here is the circuit file. You can simulate this circuit and take a look at the results. To conclude, we have seen the advantage of a Schmitt trigger as a comparator. We have also looked at waveform generation using a Schmitt trigger. In the next class, we will continue our discussion of the Schmitt triggers. Until then, goodbye.